We're going to start chapter 4 today, and chapter 4 is about quantities in chemistry. They kind of made up their own unit because, again, atoms and molecules are so tiny. There's no way you can, put them on a scale and measure them. So they made a relative scale so that you can count and measure out things. If you want to figure out the mass of a molecule, okay, they use what they call AMU, atomic mass units. And what they did was they kind of made it into a gram scale. And we'll talk about how many actual molecules and atoms there are. But in order to do it, like for instance, if I'm doing water, water is H2O, so I have 2 hydrogen for every 1 oxygen. I multiply by their mass from the periodic table, and again, you can just use 1 and 16. You don't have to use all these numbers after, you guys. So you get 2 and 16, so 18. The molecular mass of water is 18. Okay, so the mass of one formula unit is of an ionic compound is formula mass. So you'll see molecular mass, you'll see formula mass. Molecular mass is for a compound, formula mass is for an ionic compound. Figuring them out is exactly the same. It's just what type of bonding are they, okay? So a mole, again, is the way that chemists measure. 1 mole of any substance is whatever its mass is from the periodic table. Okay, so here's my periodic table. If I'm looking on here and I want 1 mole of aluminum, aluminum has a mass of 27 from the periodic table. So if I measure out 27 grams of aluminum, I have 1 mole. Okay, carbon is 12. So if I measure out 12 grams of carbon, I have 1 mole of carbon. So that's how they use the scale, a relative scale. Now remember, I said a molecule and an atom are really tiny. They're actually in that 1 mole, that's 27 grams of aluminum, or that 1 mole, there's 6.02 times 10 to the 23rd. If you wrote that out, I think it's 602 hexillion. Big number. You can't count to that number. If you started counting now, you'd die before you got to that number. And somebody would interrupt you in between, you know that, and you'd have to start over again. But there's a guy by the name of Avogadro. Amadeus, I think is his first name. Amadeus Avogadro. He figured out mathematically how many units, how many atoms, or how many molecules are in 1 mole of any substance, and this is the number. So it never changes. So if I have 27 grams of aluminum, I have 1 mole. If I had the time to count every little particle in there, I would find out when I was done that I have 6.02 times 10 to the 23rd. So 1 mole always has this many atoms. They're like a conversion factor, okay? So when you know that this is how many atoms or how many molecules there are, and then you know 1 mole, its mass is whatever the periodic table says it is, then you know you can use those to convert from one thing to another. You can convert from moles to grams to particles, and etc. Okay? And a molar mass of a compound has the same numerical value as its molecular mass. So again, like we did with water. Okay? We said it was 18 AMUs. That's the same as 18 grams in this case when we're doing our conversions. Okay? So again, these are conversion factors. Molecular mass is the mass of all, when you add everything together. And again, we can use grams per mole instead of AMU. Okay? So to convert moles and particles, again, that's Avogadro's numbers, we use 2 conversion factors. Remember, 1 mole of any substance has Avogadro's number of atoms or molecules. If you're doing elements, it's atoms. If you're doing compounds, it's molecules. So it just depends on which one you use. It's the same number. Okay, so if I want to convert moles and mass, I use dimension analysis, where I just keep converting until I get to the place I want to do. Molecular mass is a conversion factor. 1 mole of any substance is whatever its mass is from the periodic table. Okay, so converting from mass to particles, if I want to know, let's say I have 48 grams of carbon, and I want to know how many particles that is, well, the first thing I'm going to have to do is change mass, grams to moles, and then moles to atoms using Avogadro's number. Okay, so here's how many molecules in 57.2 grams of magnesium oxide. Okay, so the first thing I'm going to have to write down is 57.2 grams of magnesium oxide. Okay, well, I got to find the mass of magnesium oxide. So magnesium's 24, and there's only 1 of them, and oxygen's 16, and there's only 1. These 2 numbers I got right off my periodic table. So the formula mass, or the molecular mass of magnesium oxide, is 40. Okay, so now I've got everything I need to solve this problem. Okay, write down what I know. 57.2 grams of magnesium oxide. 1 mole of magnesium oxide is 40 grams. It's what it weighs. So this is just like multiplying by 1. Okay, and then I want to know molecules. So 1 mole of magnesium oxide, 1 mole of any substance, it doesn't matter what it is, has Avogadro number of molecules. Okay, so to solve this, I'd go 57.2 times 6.02, and I divide by 40, and then I tack on 10 to the 23rd. Okay, so 57.2 times 6.02 divided by 40 is 8.61. And then don't forget this. So in 57.2 grams of magnesium oxide, there are 8.61 times 10 to the 23rd molecules. Okay, again, these are conversion factors. And you'll notice your conversion factors all have 1 mole in them. Okay, 1 mole here, 1 mole here. Depends on what you're looking, you know, but whatever starts here, remember, goes on the bottom. You got to get rid of it. You got to cancel it out. Okay, find the mass of 5.6 times 10 to the 27 molecules of calcium sulfate. Okay, well, first I got to find the mass of calcium sulfate. I'm going to take 1 calcium, which is 40, 1 sulfur, which is 32, and 4 oxygen. 4 times 16 is 64. So 64 plus 32 plus 40 equals 136. Okay, so now I got the mass of calcium sulfate, 136. Okay, so if I want to solve, I write down what I know. 5.6 times 10 to the 27. I didn't write out molecules, you guys, because then it doesn't all fit on one line and then it doesn't look good. I know, that's important, right? Okay, so I know that in 1 mole of any substance, I have Avogadro's number of atoms, or molecules in this case. Okay, so I got those opposite. And then I want grams, so I'm going to put 1 mole of calcium sulfate, because again, molecules are going to cancel out moles, so I'm going to put grams up here. So to solve this, I'm going to go 5.6 times 136. Then I'm going to divide by 6.02 and get that number. And then with exponents, when you have scientific notation, you subtract them because I'm dividing. So it'd be 27 minus 23. Okay, so when I take 5.6 times 136 and I divide by 6.02, I get 126.5. And then 27 minus 23 is 4. Well, I can't leave it that way. That's not in proper scientific notation. So I move it over 2 and I get 1.27, I rounded. And I moved it over 2, so I make this number 2 larger. So the mass of 5.6 times 10 to the 27 molecules of calcium sulfate is 1.27 times 10 to the 6th. Okay? All right. Another thing when you're looking at chemical reactions, we use equations to represent what's going on in the equation. Okay? They talk about kinetic energy. Sometimes you don't have, sometimes a chemical reaction won't take place. I mean, we can write it out, we can balance it, we can make sure it's perfect, but it doesn't always take place if there's not enough kinetic reaction, if the molecules aren't moving fast enough to bash into each other and change their structures. So again, we need kinetic energy in order for a chemical reaction to take place, okay? The compounds that you start with, whenever you have a chemical equation, whatever you start with, those are the reactants. Those are on the left-hand side. They're like your ingredients, okay? And what you make, what you end up with is your products, okay? Your products are, you know, they'd be on the right-hand side. The arrow means yields. So if I was doing an equation, I do my reactions first. In this case, I would do, I think, what do they got here? I don't even know. Oh, they've got O2 plus N2. Those are my 2 reactants. And suppose I'm supposed to make NO, okay? So my 2 reactants would be O2 and N2. Then I'd have yields, my arrow, NO, okay? Okay, when you have an equation, you have to make sure you represent everything that's involved. You can't leave anything out. And you have to make sure that it satisfies what they call the law of conservation of mass. In other words, matter cannot be created or destroyed. So you balance an equation to make sure that there's the same amount of stuff on both sides. Okay, if you look here, there's 2 hydrogen, there's 2 hydrogen. There's 1 carbon, there's 1 carbon. And there's an oxygen here and 2 here. That's 3. Well, look at that. There's 3. So it's like this half versus that half, okay? They don't have to be you know, like here the O3 doesn't have to be together. In this case, it's split between two. Okay, so whenever you're doing an equation, you get your reactants and your products, and then you have to make sure it's balanced. And the only way you can balance it is by putting numbers in front, and those are called coefficients. Okay, so atoms cannot be created or atoms can't be destroyed. So nothing can disappear. Okay, if you could create something out of nothing, you'd be a bazillionaire. Okay, those guys that own like Amazon and Facebook, you'd be looking down on them because you'd have way more money than them. But you can't. It's impossible. All we do is we rearrange. Okay, when we do a chemical reaction, we just rearrange. We don't create anything. We don't destroy anything. We might make a product, but it's made from the reactants. And again, we're not making something out of nothing. Okay, so we have to satisfy the law of conservation of mass. And again, matter cannot be created or destroyed. All we can do is rearrange. And that's what a chemical reaction does. Okay, so a chemical reaction, again, describes, when you have a chemical reaction, you describe it by writing out a chemical equation. And a chemical equation tells you what you have, what you started with, your reactants, what you produce, what's your products, and their proportions. And that's what the coefficients in front are. Okay, so reactants and products are represented by their formulas. Okay, so you don't have to write out, you know, and you can write H2O instead of writing out water, which that isn't a big deal, but some of them have really long names. So it's much easier just to write their chemical formula. Okay, we know that reactants on the left, that's what you start with, and products are on the right, that's what you make. And they separate by an arrow. Okay, so you'd read, the reactants yields the products, is how you'd read it. Okay, here's an example. CH4 is methane, oxygen, so I'd say CH4 plus oxygen, or you could say CH4 plus 2 moles of oxygen yields carbon dioxide and 2 moles of water. Okay, that's how you would read that. Okay, all right, look at my time, I've got 2 minutes here. Okay, the law of conservation of mass and balancing equations, again, we use numbers in front. We use coefficients, and they indicate the molar ratio of the reactants and products. And that's the only way you can balance equations. You can never change the subscripts. If you change the subscripts, you got a new substance that doesn't belong in that equation. So don't make H2O H2O2, because you just change water into hydrogen peroxide, and that's not what we're looking for. So make sure you leave the formulas alone, and then you put coefficients in front to balance equations. Okay, again, on this one, what they did was, okay, there's one carbon, there's one carbon, there's 4 hydrogen, so I put a 2 here to get 4 hydrogen. Okay, now I've got 2 oxygen here and 2 oxygen here, that's 4, so I put a 2 here to get 4. And when you balance an equation, remember, you break it in half. It's this half versus that half. Okay, they have to be the same. Okay, so a chemical equation that contains coefficients, these numbers in front, those are used to make sure that the equation's balanced. The reason why we balance equations is to satisfy the law of conservation of mass, which says mass cannot be created or destroyed. So the same amounts have to be on both sides. And if you look, we have 1 carbon, we have 1 carbon. We have 4 hydrogen, 2 times 2 is 4 hydrogen. We have 2 oxygen here, and we have 2 oxygen here, that's 4. By putting a 2, we have 4. So we have the same amount of stuff on both sides. Okay, and that's how you write out a balanced equation, by using coefficients, numbers in front. Don't ever change numbers here. Don't change the coefficients. I mean the subscripts, excuse me, because now you're making a compound that's different than what was actually involved in the equation. Okay, and we're just about done, you guys, so I think the next slide is, yeah, we'll pick up on more about balancing equations on the next part of it, but we're going to quit right here. And remember, there'll be some worksheets on the bottom that have the answers if you need to practice. This section, we're going to do more on the moles and that kind of stuff, okay? So anyway, we'll finish this part, and then we'll go on to the next part later.